So, welcome to lecture 6.6 covering exponential and logarithmic equations. Now, there's not much background information in this section for us to cover because all of that's been covered in the previous 3 sections since we've been learning about logarithms. Well, and actually the previous 5 sections, including exponentials as well. So this is kind of the culmination of all of that information that you have received in those sections, allowing you to utilize that knowledge to solve these types of equations. So the first type of equation that we encounter in this section are exponential equations that can be or already are written as like bases. So the only thing that we have on either side of the equal sign are exponential expressions of like bases or exponential expressions that can be written as like bases. So let's just go ahead and jump into solving these. And the property that we have to understand to be able to do so is that when I have base b raised to a particular exponent equaling that same base b raised to some other exponent, I can equate the exponents. So that is the strategy we're going to use for these next 3 equations. Okay, so I start out with 5 raised to the 2x power, and that's equaling 5 raised to the 3x plus 2. Since my 5s are like bases, I can then say, well, if this is true, if it's true that these 2 things are equal, then I know 2x has to equal 3x plus 2. And then I'm going to subtract 3x from both sides. And that leaves me with negative x equals positive 2. Divide both sides by negative 1. And I get x is negative 2. And you can plug it in mentally and give it a check. If I plug in negative 2 on the left-hand side, that's 5 to the negative 4th power. And if I plug in negative 2 on the right-hand side, that's 5 to the negative 6 plus 2, which is also 5 to the negative 4th power. So that's how that works. Let's go ahead and do this next one. Notice on this right-hand side, I've got a 3 to the 2x divided by a 3 to the understood 1st power. So I need to use my exponent rule so I can write that as an exponential expression of base 3. So my right-hand side for right now is going to remain 3 raised to the 4x minus 7. And using my exponential properties, I know that this right-hand side can be rewritten 3 raised to the 2x minus 1. When you're dividing like bases, you subtract their exponents. That is the exponent property that we use there to rewrite the right-hand side. Now that I have both sides as a single exponential expression raised to particular exponents, I can equate the exponents. 4x minus 7 is equal to 2x minus 1. Now I simply solve the linear equation. So I'm going to subtract 2x from both sides and add 7. And that leaves me with 2x is equal to 6. Divide both sides by 2. And my solution here is x is 3. Okay, and the last one on this page, 256 and 4 are both base 2, can be written as base 2 exponents. So 256 is 2 to the 8th. 4 is 2 squared, but that 4 is being raised to an x minus 5. So I basically have 2 to the 8 equals 2 times, okay, so when I'm raising a power to another power, here's another exponent rule, I have 2 times x minus 5. And I need to distribute that 2. So I now have 2 to the 8 equals 2 raised to the 2x minus 10. And now that I have exponential expressions of the same base on either side, I can equate the exponents. 8 equals 2x minus 10. I'm going to add 10 to both sides. And that gives me 18 is 2x. Divide both sides by 2. And I get x is 9. And you could certainly plug it back up into the original equation to check it. Okay, another couple of problems here. So we have 2 raised to the 5x power equals the square root of 2. Well, I want to get this into an exponential expression. So that's the same thing as 2 to the 1/2 power, which means 5x is equal to 1/2. I'm going to divide both sides by 5, which is the same thing as multiplying by 1/5 on both sides. And that leaves me with x is equal to 1/10. And then this last one, they threw this one in here to keep reminding you about being able to use your calculator to solve equations by graphing each side of the equation. And we can see that this blue exponential part is the left-hand side of the equation. This is 3 to the x plus 1. And then I've got y equals -2 hanging out down here. You can see that these functions are never going to intersect each other. So there's no x value where those functions are equal. So there is no solution here. You can either write out no solution or we have the no solution symbol. Okay, solving exponential equations using logarithms. So just a general rule of thumb, most of the time you use logarithms to solve exponential equations and exponential functions to solve logarithmic equations. So this is an example, or these three are an example of using logarithms to solve exponential equations. And what we do is we start out with our exponential equation, 5 to the x plus 2 equals 4 to the x. You can see there's no way to write those two sides of the equation as like bases. So that's why we have to have other methods of solving these things. And this method that we are learning is to take the log of both sides. And you'll recall that when you take the log of an exponential expression, that exponent can come out front as the coefficient. So we found a way to get that variable down out of the exponent. And so now I have x plus 2 times the log of 5 equals x times the log of 4. All right. And I need to get my variables on one side of the equation and my logarithms on the other side of the equation. But I have to be able to split off any constant terms from this. So you have to be a little bit clever with these types. You'll actually want to distribute that log of 5. And so now I have x log 5 plus 2 log 5 equals x log 4. And so I need to get my variable terms on one side, so I need to subtract that x log 4. And I need to get my constant on the other side, so I'm going to subtract 2 log 5 as well. So there's my x log 4, 2 log 5. So on the left-hand side, I have x log 5 minus x log 4 equals negative 2 log 5. I'm going to need to give myself a clean page to finish working this problem. I did not plan this room very well in here, so I'm going to take a picture, open up a new page, paste it here, and we'll continue. Okay, so here's where we are so far. All right, here is another piece that you have to be clever about, factoring. So if you notice on the left-hand side, if I'm trying to isolate my variable, I have a factor of x in both of those terms. So I pull that x out front as a GCF, and then I'm left with log 5 minus log 4, and that equals negative 2 log 5. And now I divide both sides by log 5 minus log 4. To isolate the variable. Okay, so when we get here, this solution equals negative 2 log 5 divided by log 5 minus log 4. But it can actually be more difficult for people to put this into their calculator and estimate the solution than it is to actually find the exact solution with our algebraic means here. So I'm going to write on the screen here exactly how I would type this into my calculator to get the correct answer to come out. So I'm going to type, I need to hold all that in the numerator together. So parenthesis, negative 2, I hit my log key and it opens up a new parenthesis 5, close my log, close my numerator, divided by, open parentheses for your denominator, log, it's going to open the parentheses, close the log there, minus log, it's going to open parentheses, close the log, close the denominator. And so let me put that into my calculator to estimate what we should get. Log 5 minus log 4. And I get approximately negative 14.4251, and that's approximate. So we could check it. Now, we're not going to get an exact answer here, but we can get very close to check it. So 5 raised to the negative 14.4251 plus 2 should equal 4 raised to the negative 14.4251, or be very close to it. So 5 raised to the negative 14.4251 plus 2. When I put that into my calculator, I get 2.066463.787 times e to the negative 9th. That means you'd have to take your decimal place 9 places to the left. So this is a very, very tiny number. And let's see what I get when I do 4 raised to, hang on just a second, 4 raised to the negative 14.4251, and I also get 2.0664. Actually, it starts becoming a different number in the, let's see, millionth place it looks like. So I'm getting, for that right-hand side, 2.06644705 e to the negative 9th. So practically the same number. The reason it's not exactly equal is because we estimated and truncated that number when we put it into our calculator. All right, let's go back and grab that next problem. And I am assuming that I'm going to need more room for this one as well, so I'm going to go ahead and grab it and put it on a new page. Okay, so we start with 2 to the x equal to 3 to the x plus 1. So I'm just going to rewrite that so we can get going with it. Okay, so 2 to the x equal to 3 to the x plus 1. Once again, I cannot write them as like bases, so I take the log of both sides. I could also take the ln of both sides. It doesn't matter. And once those are in logarithmic form, those exponents can come out front as coefficients. So this is x log 2 equals x plus 1 times the log of 3. So again, you'll want to distribute that log 3. So x log 2 equals x log 3 plus log 3. Need to get my x terms on the same side, so I'm going to subtract x log 3 from both sides. And I'm left with x log 2 minus x log 3 equals the log of 3. Factor out my x. Trying to get that variable by itself, I'm left over with the log of 2 minus the log of 3 equals the log of 3. Divide both sides by log 2 minus log 3. And you're solved for. So I get that x is exactly equal to the log of 3 divided by the log of 2 minus the log of 3. And you could put that into your calculator and estimate and check it and all that. For the sake of time, I'm going to skip that with this one. And finally, the last one on this page, 2 to the x equals 3 to the x. I might have room for this one. I'm going to try to do this one on this page here. So I'm just going to scratch that out. All right, so I'll start here. 2 to the x equals 3 to the x. Take the log of both sides. Both of those exponents come down as coefficients. So I now have x times log 2 equals x log 3. I need to get my variable terms on one side, so I'm going to subtract x log 3 from both sides. And now I get x log 2 minus x log 3 equals 0. Factor out my x, and I'm left with log 2 minus log 3 equals 0. Divide both sides by log 2 minus log 3. Well, 0 divided by anything is just 0. So I end up with x is 0. Now, look back up here. If I have 2 raised to the x power equaling 3 raised to the x power, I can only insert one value at a time into the x. And the only way that those two things are ever going to be equal is if they are equal to 1. And anything raised to the 0 power is equal to 1. So 2 to the 0 is 1, 3 to the 0 is 1. Okay, now if we're given an equation with an e in it, the natural base e, we can take the ln of both sides and end up with some pretty simple equations to solve, because whenever I take the ln of e, that's always 1. So let me write that down at the top so we remember this. The ln of e is equal to 1 because that's the same thing as log base e of e. And this is asking me, what can I raise e to get e? And that's 1. So anywhere we encounter log base e, the ln of e, we can just change that to 1. So we'll do that in these types of equations when it gets to that point. Okay, so what you do want to do first, so here we start out with 100 equals 20 times e to the 2t. You want to isolate your exponential expression. So I'm going to divide both sides by 20 first to isolate. And 100 divided by 20 is 5, and that's equal to e to the 2t power. So I need to get that variable out of the denominator, and to do so, I'm going to take this time the ln of both sides. Now you can take the log of both sides here, but whenever you're dealing in base e, it's very nice to take the ln, and I'll show you why right here. Now that 2t can come out front as a coefficient. So I have 2t times the ln of e, and I just showed you at the top, the ln of e is just 1. So that's 2t times 1. So the ln of 5 is equal to 2t. All I need to do now is divide both sides by 2. And I get t is equal to the ln of 5 over 2. Okay, moving along. I need to start by isolating my exponential expression. So I'm going to subtract 5 first. And that gives me 4 times e to the 2x equals 7. Then I need to divide that 4 off of both sides. You got to get that exponential expression completely isolated before you can take the log of both sides. You don't have to, but it makes your life easier, I promise. So e to the 2x equal to 7/4. Now I'm ready to take the ln of both sides. So don't forget that my exponent comes out front as the coefficient, and the ln of v is just 1. So this entire left-hand side is just 2x equals the ln of 7/4. Then I just need to divide both sides by 2. X equals the ln of 7/4 divided by 2. Actually, these last two answers, you're not going to see them written this way in WebAssign. We know that there's an understood 1 being multiplied by both of these ln's. So they're actually going to write these answers as 1/2 times the ln of 5, and this one's going to be 1/2 times the ln of 7/4. Okay, so just be aware that there can be different forms and ways to write these values. All right, so I need to isolate my exponential expression, but I have exponential expressions of base e on both sides. So what I'm going to do is start out by subtracting e to the 2t, and that's an understood 1e to the 2t that's being subtracted from both sides. Since my right-hand side is 7e to the 2t, those are like terms, so I can actually combine those. So this is 3 equals 6e to the 2t. Now I still need to isolate by dividing both sides by 6. So I get 1/2 equals e to the 2t. Ready to take the ln of both sides. That 2t is going to come out front as a coefficient, and the ln of e is 1. So the right-hand side is just 2t. Left-hand side, ln of 1/2. The ln of 1/2 is the same thing as the ln of 1 minus the ln of 2. That's using our quotient property of logarithms. Well, the ln of 1, that says what can I raise base e to get 1, and that's 0. So this whole thing is just 0. So I have negative ln of 2 equals 2t. Divide both sides by 2. And my final solution, t is equal to negative 1/2 ln of 2. Okay, extraneous solutions. Sometimes the methods that are involved in solving these types of equations produce what we call an extraneous solution. This is a solution that shows up when you solve these equations properly. However, it ends up that you're taking the logarithm of a negative value when you plug it back in, so it's not truly a solution. So in these cases, you have to discount these types of solutions that come up and only take the solutions that will produce real number values. So we're going to have to dig way back to where we learned how to use substitution with quadratic equations. This was the very first section we studied in this course, 2.6. So the first thing I'm going to do is get this equation equal to 0. So e to the 2x minus e to the x minus 56 equals 0. I'm going to use substitution. I'm going to call u e to the x. And then if I substitute u in, I have u squared minus u minus 56 equals 0. So now I have a very simple quadratic trinomial to solve for. So u minus 8 times u plus 7 equals 0. So this means u minus 8 equals 0, or u plus 7 equals 0. Here u is 8. Here u is negative 7. So if I substitute back in e to the x, I have e to the x equals 8. E to the x equals negative 7. Well, I can stop right here with e to the x equals negative 7 because there's never going to be an exponent that I can raise e to or any positive value to and get a negative value out. So this is an extraneous solution that showed up. We need to solve for x on this other one, so I'll take the ln of both sides, and I end up with x equals the ln of 8. That's my solution, my one solution. Same type of equation here on the right. I'll go ahead and say I'm going to substitute e to the x with u, get my equation equal to 0, e to the 2x minus e to the x minus 2 equals 0. Substitute u squared minus u minus 2 equals 0. So u minus 2 times u plus 1 equals 0. U minus 2 equals 0. U plus 1 equals 0. U equals 2. U equals negative 1. So here, e to the x equals 2. E to the x equals negative 1. I can go ahead and discount this solution as being extraneous, and then I come and solve for this one over here. X comes out front as the coefficient. ln of e is just 1, so x is equal to the ln of 2. Okay, so solving logarithmic equations using the definition of a logarithm. So basically what this says is if you can manipulate your equation so that it equals a single logarithm equaling a single value, then you can turn it into exponential form to solve the equation. And I'll just remind you, to turn it into exponential form, you start at the base, raise to the is, and that equals the of. So you want to get it in that form first. So with this first one, I'm going to subtract 6 first. And that leaves me with the ln of x equals 4. Well, that's the same thing as log base e of x equals 4. So if I start at the base, raise to the is, and equal the of, that tells me e to the 4th power is x. That's it. With this next one, I need to divide 2 off of both sides to isolate that logarithmic expression. And that gives me the ln of x plus 1 is equal to 5. I'm going to rewrite that log base e so I can change to exponential form. So this says, I start at the base, raise to the is, equal the of. That means e to the 5th is equal to x plus 1. Going to subtract 1 off of both sides, and I get e to the 5th minus 1 is equal to x. And then finally, they're once again reminding us, don't forget, you can use your calculator to solve these. So if I put 2 to the x as y1, and 1,000 as y2. I have 2 to the x that comes up like this, and it intersects with y equals 1,000. And I get that x value as being approximately, and don't forget you put them both on the same set of axes, and then you do second and trace, which is your calculate menu, go down to intersection, Curve 1, curve 2, don't worry about guessing, just hit enter and it will tell you that that x value is approximately 9.97. Okay, using the one-to-one property. What the one-to-one property of logarithms says is that if I have the log of a certain base b of s equaling the log of that same base, those are the same bases, equaling t, then I can call the two things I'm taking the log of equal. Now, I'm not going to use this property to solve the first one. I'm actually going to work through all the work for it so you can see that it actually does work. And then on the second one, we'll just use the property to make it nice and neat and quick. Okay, so the first thing I notice is that I can pull this exponent out as a coefficient. And that gives me two times the ln of x, and I'm going to get this equal to 0, so I'm going to subtract the ln of 2x plus 3, and that's equaling 0. Don't forget that, actually I'm gonna start over on this. Do over. Not going to pull that x squared, or that square down. I'm just going to subtract so that I can use my quotient rule and combine those into one logarithm. So the ln of x squared minus the ln of 2x plus 3 equal to 0 now. My quotient property of logarithms says that this is the same thing as the ln of x squared divided by 2x plus 3, and that's equaling 0. So that's log base e of x squared over 2x plus 3 equaling 0. So e to the 0 equals x squared over 2x plus 3. E to the 0 is 1. X squared over 2x plus 3. I can use cross multiplication now to say that 2x plus 3 is equal to x squared. Get it equal to 0 by subtracting 2x and 3 from both sides, since it's a quadratic. So 0 equals x squared minus 2x minus 3. 0 equals x minus 3 times x plus 1. So I'll come up over here to finish, and I'm just going to do this because I know I won't need much room for that side. So x minus 3 equals 0, x plus 1 equals 0, x is 3, x is negative 1, and when you plug both of them in, you get true solutions for both of them. Let me just double check that. ln of negative 1. I do not think that you get, I don't think negative 1 can be a solution. Let me double check this. Your book said that it could, but I don't know that they checked it. Let's check negative 1. So the ln of negative 1 squared equals the ln of 2 times negative 1 plus 3. Yep, this is no-go on that solution. Although this is the ln of 1, this is the ln of negative 4 plus 3, which is negative 1. And you can't raise e to any value to get a negative number. So book had a mistake in it. Negative 1 is not a solution there. 3 should be, though. We should be able to. I'll show you real quick. The ln of 3 squared should equal the ln of 2 times 3 plus 3. So the ln of 9 equals ln of 6 plus 3, which is 9. So we're good to go with 3, but no go on -1. So it's always important that you check these solutions. Okay, so this next one, we'll just use this property. Since I'm taking the ln of both sides and I have nothing else going on, I can go ahead and say x squared equals 1. I can equate what I'm taking the log of. X squared minus 1 equals 0. This is x plus 1 times x minus 1. That's a difference of squares. X plus 1 equals 0. X minus 1 equals 0. Here x is -1. Here x is 1. And both of these solutions do work, because watch what happens. Even the -1, if I take the ln of -1 squared, equaling the ln of 1, -1 squared is 1, so the ln of 1 is the ln of 1. And same thing with +1. So we're good with both of those solutions. And finally, a word problem to finish us off. This is about radioactive decay. So for those of you going into chemical or biological sciences, this concept will be very important to you. And we have a formula for radioactive decay. And I'll just write that formula bigger. A of T equals A sub 0, which is the initial amount of whatever substance you're working with. It's that initial amount that's present. And that's multiplied by the natural base E raised to the ln of 0.5 divided by capital T, which is the half-life of the substance, times the time that that thing has been decaying. Okay, so the half-life of the substance is the time it takes for half of that substance to decay. So we are given the problem of figuring out how long it will take 20% of a 1,000 gram sample of uranium-235 to decay. So here's the information for uranium-235. Uranium-235 has a half-life of 703,800,000 years. So we just need to plug in this information into our formula and solve. So I want to end up, I want to know how long it takes 20% to decay. So how long will it be before I'm left with 80% of my original 1,000 grams? So on the left-hand side, I want to know, when will this thing equal 80% of 1,000? The sample that I begin with is 1,000 grams, and I'm multiplying that by E raised to the ln of 0.5 divided by big T is the half-life of the substance, so 703,800,000 times T, and I'm solving for T. Okay, so 80% of 1,000 is 800. So I'm trying to figure out, when will I be left with 800 grams? E to the ln of 0.5 divided by 703,800,000 times T. I'm going to divide both sides by 1,000 to isolate my exponential expression. And 800 divided by 1,000 is 0.8. So I get 0.8 is equal to E raised to the ln of 0.5 divided by 703,800,000 times T. Now I'm ready to take the ln of both sides. And don't forget, when I do that, that allows me to pull my entire exponent out front as the coefficient, and the ln of e is just 1. So what I have so far is the ln of 0.8 is equal to the ln of 0.5 divided by 703/800,000 times t. And I multiply both sides of the equation by the reciprocal, 703/800,000 divided by the ln of 0.5, both sides, to get that off of the variable. So 703/800,000 divided by the ln of 0.5. And when I put that entire left-hand side into my calculator, so this is how I'm going to put it in. I'm going to open a parenthesis for my numerator, and don't forget, when you multiply fractions, you multiply straight across. So my numerator is going to be 703/800,000 times the ln of, you can put 0.8. It's going to open a parenthesis, or you can just put 0.8. Close off my numerator and divide that by the ln. It will open a parenthesis and put 0.5, close that parenthesis. And you get that the time is approximately, okay, so this is the time it's going to take for only 20% of that uranium to decay. And that is 226,572,993 years. All right, that's all I have for you on solving logarithmic and exponential equations. I hope this was helpful for you.